Hi Neeraj, how?
Good evening, sir.
Could anyone let me know if I am audible or not?
Yes, sir.
Good evening, sir.
Good evening, very good evening. So let us start the session with DC machine we were discussing in the last session, right? So we will extend that topic with keep with winding configurations, right? It is very important that how do you wind your DC machine, right? And what are the effects of various types of windings on the machines? Okay, so when you want certain kind of output, what would you prefer basically? Would you prefer lap winding, wave winding? How many poles? Why number of poles are important, and how it will affect the machine's performance? That we will see with some problems, right? Let me share the screen. Yeah, so I hope you are able to see my screen and you are able to see the first question as well.
Yes, sir.
Great. So in this problem, it is asked that it is a DC machine, okay, with 8 poles, and rated current is mentioned as 120 amps. How much current will flow in each path at rated conditions if the armature is a simplex lap wound, duplex lap wound, and simplex wave wound? Okay, so I hope you are aware of the terminology of lap winding and wave windings.
Yes, sir.
Okay, so could you please let me know what do you mean when we say lap winding, and what do you mean when you say wave winding?
Sir, in lap winding, the adjacent coils are connected to the adjacent commutator segment, sir.
Okay, yes, that is correct. Yeah.
And in case of lap windings, we get as many parallel paths as there are number of poles. But in wave winding, we only get two parallel paths. However, maybe the number of poles. It doesn't matter.
Saying in lap winding, let me write it. In lap winding, we get number of parallel paths is equal to number of poles. Okay,
Yes, sir.
and okay, so it is a very important conclusion from the lap winding. So why is so that we have to connect that much of parallel paths equal to number of poles, and what are the advantages of that and what are the drawbacks of that? If you have any idea, anything you want to say.
Sir, the advantages of lap winding could be that the sir, current is divided in parallel paths. Therefore, it is reduced, and so the amount of insulation required is reduced.
Hmm.
Money is saved, and there is less
Okay.
mechanical stress on the shaft, which holds the armature.
Okay. Yes. Yes. Good. These are good enough reasons.
Uh, Disadvantage points.
So yeah. Yeah. Go ahead.
No, sir, I can't remember any disadvantages.
Okay, okay. So you mean that lap winding is advantageous.
Yes, sir.
Okay. Deepak, do you agree with mirrors or do you have any other thing?
But sir, as he said, the insulation will be less, but insulation is depend on voltage, not current. I think.
Yes, yes, yeah, that is correct. But the thing is, yeah, insulation requirement might be same. Okay, I'm not saying certainly might be same, but you are reducing current in each winding, right? In each winding, so essentially you are reducing the current and you are reducing the I square R loss from that particular turn or that particular path. So from each parallel path or in each coil, right? So in that sense, you can say that yeah, your heat heating is getting reduced, but yeah, insulation will be same. Insulation level will be same. It will not depend on the current level. It will depend on the voltage. That is correct. Yeah, Deepak. Any other thing?
And sir, according to me, lab
Hmm.
binding is advantage where we required we need to more inject more current from the source, and we want to distribute in our armature circuit
Okay,
because there are
so
small number of
basic.
parallel paths. Yes, sir. Go.
But any other advantages of parallel paths because you are paralleling the coils. So what is happening? Your EMF will be same.
Yes, sir. And sir, speed will constant, I think.
Okay, EMF will be constant. You are saying. Okay. So let us suppose you have two parallel paths. Okay, with two coils each. These are your terminals. Okay, let us suppose each with one turn. Okay, so one turn with two parallel paths. And I want to reconfigure this configuration. Okay, I want to reconfigure this configuration with four parallel paths. How can I do so? Is it fine? Have I reconfigured correctly? Or did I leave anything? Okay, now again
Yes, sir.
one turn, one turn. Okay. So now could you see anything? Let me also indicate the current. Okay, this is armature current. This is your overall voltage. Now your current will be divided into two parts, IA by 2 and IA by 2. And here also IA is there plus minus VT. Now here each. Okay, so I will indicate with VT1 and VT2 to differentiate between two different circuits. Okay, so since it is a parallel path, its parallel path is 2 in first circuit. So let me call it that it is connected with wave winding. However, lap winding is also possible, but let me call it wave winding to differentiate or to highlight the advantages and drawbacks. And here I am calling it lap winding. Okay, so I hope it is clear till now. So what do you visualize here?
Sir, in the second case, the terminal voltage will be reduced, sir.
Yes, yes, that's what I wanted to point out. So terminal voltage will reduce, right? Your voltage requirement will reduce. If you are doing parallel of the branches, parallel of the coils, you are essentially reducing the voltage, and that's the whole point of doing all incorporating so many parallel paths. Because in many applications, you would have the restriction on voltage, right? You cannot apply as much as of voltage as you want. So in such cases, you would have to do the paralleling of your coils, right? So if let's say your what to say, okay, another first let us discuss what are the consequences, and then we will uh, go back on the application perspective. Okay, so here uh, EMF is reduced. One thing we concluded, EMF will be reduced. Okay, any other thing? VT will be reduced. Let me conclude it. VT, terminal voltage will be reduced. So what will happen if terminal voltage will reduce and same current you are applying? IA and IA both are same.
Sir, power will be lower.
Yeah, if same
Sir,
RC
current will
current you are
reduce.
applying, currents are same. In currents in parallel paths are reduced. Okay, so currents. Let me write it. Current in parallel paths are reduced. But when your supply current is same, when supply current are same in both cases. Okay, and when supply currents are same, what is happening? Your terminal voltage is reduced, your supply currents are same, so power input and as well as output power both will be reduced. Okay, so to provide you want to have same output power, you need to double the current. Okay, so here is the catch. It is not as much as green as you are imagining, that you are paralleling and you are reducing the current as you are. That's all. Your power will be reduced. So again, what you have to do, you have to multiply with two times of current. Finding IA by 2, IA by 2 as of the original, it will be there. So in low voltage, high current, okay, let's conclude it. If you have certain application, low voltage, high current, you can go ahead with lap winding with
Sir, I have a doubt.
multiple. Go ahead, please ask.
Sir, how you reached the equivalent circuit of that wave winding with the two coils in a path?
Your voice broke down.
Sir, how did you draw that wave windings equivalent diagram with the two coils in two conductors in one line? Can you again
Okay, so
explain that?
okay, so in wave winding, actually it could be lap winding as well. I wrote at the place of lap winding, wave winding for the reason I want to highlight the differences between them. So in wave winding, you might be knowing that you cannot increase the number of parallel paths greater than two, right?
Ah, yes. Hello,
Are
sir.
the configuration. Yeah. Do you know the fact that in wave winding, number of parallel paths cannot increase by two.
Yes, number of poles is always equal to 2
Huh?
in wave winding.
No. Why? Because number of parallel paths, or the configuration of windings is kind of wave. It is continuous, right? So you have to wind it the whole machine at once. But in lap
Yes,
winding, what you can do, you can make it multiple coils, okay,
yes,
and like that it can go, right?
yes,
Yeah, so here you have the control on the number of parallel paths, right? From wherever you want to get the terminal out of the machine, you have the control on that. But in wave winding, unfortunately, you have to bear with two parallel paths. So that's the thing. Right. So hence I told that in wave winding we have two parallel paths, but we have same number of turns. Right. We are not tampering with the number of turns because we want equal amount of flux in both the machines. Okay. So for equal amount of flux, we want equal amount of MMF supply, and that can be done with the same number of turns and same number of current. Do you agree? Sorry, same amount of current. Do you agree?
yes, sir.
Yeah. So that's why I drawn in lap winding four different turns in four parallel paths, equivalent of two different turns in two parallel paths of lap winding. Right? Is it clear? Or any other doubt is there? We can clear it out. Right? I'm not able to hear you, Adil. Could you please let me know? Or if you are not able to speak because of internet connection, you can type in the chat box.
Okay, sir. I understood.
Okay. Okay, great. Thanks a lot. So yeah, so we were concluding what are the advantages and disadvantages of lap winding and wave winding. Okay. So as you see that if you want to have an equivalent of wave winding, okay, with the same power, yeah, your voltage requirement will be reduced, but at the same time, your current requirement will increase with the same ratio, right? So that's the catch. You will not get anything in free. You have to pay in terms of current. However, uh, there are certain applications where low voltage are desirable, and there are very sophisticated technology requirement in high voltage. So in such cases, it reduces our effort in handling high voltages. So in such cases, lap winding you can use, or even uh, in high voltage also you can use lap winding with two parallel paths. So that is nothing but essentially your wave winding, right? So that we can conclude here. And for high voltage, low current, wave winding is preferable. Okay, so we have concluded it very conveniently, but there is again a catch here. Okay, what is the catch? So, if it is so convenient, why don't we increase, very high number of parallel paths? So, such that your voltage will be reduced to very nominal level, and you would be able to generate the same power. So, is there any drawback in increasing the number of parallel paths, or it comes at, without any drawback? Can you have as much of number of parallel paths as you want, or you have to restrict it at some point, or or would you face any problem if you increase the number of parallel paths?
Sir, I think there should be a restriction because the space available to put the brushes is limited, sir.
Yes, that is true.
The
Space is limited, but anyway, we can reduce the width of commutator, okay, and brushes, so that if let's say we are able to do that, so in such case, can we incorporate high number of parallel paths?
Sir, I think there is a I square R losses also maybe considerable amount of occur.
I square R loss, you are saying that will be increased, you are saying?
Yes, sir. That will be
Mm,
considerable amount, so we have to, I think, restrict.
I don't think it will increase. Let us see what will happen to I square R loss. Okay. So here in four parallel paths, okay, we have, you know, IA by 4. Okay, so if you are providing 2 IA, then it will be IA by 2, right? So IA by 2. IA by 2 square into R. Okay, so if you are doing such thing, then it will come out to be, and it will be multiplied with 4. Okay, so it will be equal to IA square by 4 into R term. IA square by 4 into 4, so it will be essentially IA square into R term. Okay, let us see what will happen in the case of wave winding. So again, we have IA by 2 a square into 2R term. Do you agree here it will be 2R term instead of R term because there is only one term into two parallel paths, so 2 times I will multiply. If you do not get at any point, please stop me and we will clarify that point. Okay. So essentially it will be I square by 4 into R term. So again it will come out to be same IA square R term. So essentially it doesn't matter how many parallel paths you are connecting, your losses would be same. I square R losses would be same because your the distance of each turn will be same. It will not change. Is it clear, Deepak?
Yes, sir. Thank you.
Okay. So let me, if you are able to recall the parallel operation of the transformer, okay. So what was the drawback there? What was the major drawback in the parallel operation of the transformer? And how did we avoid that, right? So
there
first
was a
thing,
risk of circulating current.
circulating current, yeah. So as you will go ahead with paralleling the coils or paths or windings, you will have to face the issue of circulating current. It is inevitable. Okay, you cannot avoid it. It will be there. So how to deal with that? Do you agree? Everyone agree that circulating current will flow? And why does it flow? Because it is very difficult to maintain the exact amount of induced voltage in each parallel path. So there is even a slight mismatch is there. A circulating path or a circulating current will start flowing in the path, right? So
Okay, sir.
it was very major problem. Yeah, Neeraj, you are correct. You are correct that circulating current is there. So it arrived in earlier days, and people had to find certain solution. Without some solution, how could have they proceeded with such machine if such machine is having circulating current? So in machine you cannot avoid circulating current because it will induce huge amount of losses, as well as, you know, if you are trying to control, because in DC machine you might be aware, or if you are not, we can discuss that topic as well. As you load the DC machine, what happens? Your magnetically neutral axis gets shifted to geometrically neutral axis, right? MNA MNA shifts some angle away because of armature reaction. Okay, that's why there are some sparking happens, and the proper positioning of the motor is not possible. We cannot maintain the machine or the armature at a certain position for a long time. So due to that, a spark occurs. So there are certain scenario where your winding can be burnt or temperature may rise. And on top of that, circulating current also flow in the winding. That will be disastrous, right? So there has to be a solution, and that solution is the equalizer. Okay. So what they did, they connected all the windings to the equalizer, okay, such that any circulating current will flow through the equalizer and get out of the windings in the overhang section, right? So let me draw it for you. How does equalizer get connected? Okay, so it has certain kind of shape. Let's suppose you have this kind of two parallel paths or so. So these are the equalizer bars, okay, through which circulating current will come here and go through these paths. Okay, so it helps in reducing the circulating current, and it will not interfere with any other any other paths, right? So essentially what we are doing, we are eliminating the risk of circulating current, and because of circulating current there will be high losses that will occur in the machine, because circulating current might be a small, but because of that a small current, that difference will be cumulative. So in that way it will increase the losses. So that's how we eliminate this circulating current in the DC machines, right? Is it clear?
Sir, please explain it a little bit more, sir. Construction and where it is placed in the machine, sir.
Okay, so where it is machine, it is it is present at the commutator. Let me see if I have any picture. So okay, I have brought some pictures of that. It will take certain seconds to get refreshed. I hope you're able to see the.
Yes, sir.
Yeah, sorry, I got disconnected somehow. Am I audible right now?
Yes, sir.
Okay. So are you able to see the picture?
Yes, sir.
Okay. So from configuration you can see, but from the physical machine, you might not be able to point out where are they connected. Okay. So you know that number of commutators are equal to number of slots, number of armature slots, right? So that many commutators are there, and the number of brushes, how many will be there in the machines? Number of brushes is equal to
Number of poles for lap winding.
okay, number of brushes is equal to number of poles for lap winding, and for wave winding
2.
2. Okay, so in the picture shown, it is a motor in earlier days designed by General Electric. You can find it online as well. So this motor has 4 equalizer bars connected at the commutator. So you can see 4 equalizer bars here. And this is the commutator section which you are able to see in the figure, right?
Okay, sir.
So did you get the idea how do we connect this, right? And with on the commutator brushes will be connected. So when commutator and armature will rotate, so current will, whatever the equalizer, oh sorry, whatever the circulating current will flow, that will go through this equalizer bus. Okay then. So I hope you got the idea, and it can be asked anywhere, right? First thing is that you have to be aware with circulating current in the DC machine. Were you aware earlier? Anyone?
Yes, sir.
And okay, you were aware, right? So uh, in did anyone go through this week's lecture by professor? In any case.
Yes, sir.
Okay, so there it was mentioned all circulating current and how to avoid.
No, sir.
Okay,
I think
so
it will be in the
oh,
coming lecture, sir.
okay, so it might be in upcoming weeks. So anyway, so these kind of things will help you if you go for certain interviews or any any practical application. If you see DC motors, so you might appreciate at that time. Okay, so but our goal is here to solve the problem, but behind the problem, what is happening, that is again very important, right? So now coming back to the problem here in the DC machine, we concluded that in lap winding the number of parallel paths are equal to number of poles, and in wave winding your number of parallel paths will be fixed to the 2, right? And we discussed what are the advantages, disadvantages, right? So the disadvantages, you all were only aware with the advantages of lap winding, that you can reduce the currents and all, but this is the drawback when you increase the number of parallel paths after a certain point, then you have to again come up with equalizer to equalize it and restrict the circulating current in the machines. Otherwise efficiency will be seriously low. Okay, so now you can have the idea of drawback of lap wind or the higher number of parallel paths. Okay, so now in the first part, how much current will flow in simplex lap wound?
Sir, 15 ampere.
15 ampere. Is everyone agree with Neeraj? if you are not able to speak, you can write in chat box also. I can read here. So Neeraj told that 15 ampere, and I guess he's correct because current is equal to current in each path is equal to the number of the amount of current that will be divided into number of parallel paths. So in simplex lap wound, what do you mean by simplex lap wound? What does this terminology states? Simplex lap wound, or duplex, or triplex, or quadruplex?
Sir, in simplex lap winding, each coil is identical.
Each coil is identical, ideally or practically as well. Each coils are identical only, otherwise there will be mismatch of voltage, right? So okay, uh, it is fine, identical, but any other thing?
Identical in terms of, sir, width, sir, the number of slots.
Okay, okay. So you see that, let me show you that you have a slot, right? And it is up to you. You can connect one coil with dot and cross, right? With n number of turns, right? Multiple turns you can wound on a single slot or single armature pole pair. So, which configuration does this particular winding have? So, we call this kind of winding as simplex winding because you had two slots, you just wounded the two slots very simply, right? No sophistication, nothing. But when you go ahead with you want to use these slots more efficiently, then what you can do, you can connect, you can place another coil. Okay, essentially it should be that way. Let me copy it first.
Sir, in duplex binding, number of parallel path is twice of number of poles.
Yeah, you are correct. But why is so?
The reason I don't know.
Okay, so region is important. Uh, it is fine that you know these relations to solve the problems. That is fine. But region also is very important in case you forgot the expression or anything. So that's why I'm drawing
Yes,
this.
sir.
And so now, okay, dot cross, mm, cross dot.
Sir,
So you
cross means current is outward.
current is inward. Cross means current is inward. Dot means current is outward. Okay, so
Okay.
inward mean let me draw the direction also of the current in each coil. So this is how current will flow here, and okay. So imagine this is in a plane. Okay, since we have 2D only, but imagine this is in plane. So one current is coming out of this dot, okay, and going all the way in this page, red one, and the white one is again here is it is coming out of the plane in this way and going to the plane in other slot. Okay, so what did you achieve by this particular configuration? Any idea what did we achieve with this kind of configuration? And it can increase to 3, 4 as well, but that would be much complex. Generally, we restrict it up to 2, but in numericals, it can be to any number. But what did you achieve with this two duplex? This is known as duplex winding or double layer winding. So earlier in one slot, only one coil was there, right? Now in one slot, you are placing two coils. So you are using the space very efficiently at the same time. Okay, at the same time in one slot, your current density might increase. Okay, it can increase because you have now higher number of turns. Instead of one coil, you have two coils. It is not anymore simplex. But again, if your current are increasing in the slot, but essentially in a coil the current is getting reduced because essentially all these coils what do they do? They reduce the current loading from the machines. So if let's say earlier one slot, one armature slot or one armature pole were capable of carrying 10 ampere, okay, and that 10 ampere would be a part of total armature current. Okay, if let's say we have, let me write down so that you don't get confused. If let us say you had earlier 8 parallel paths in simplex wound, it means your current, supply current, would be reduced in 8 parts, right? So it will be IA by 8 in each coil. Now, or each coil is, each coil, let me write it as well. Each coil means in simplex wound is each slot. Now, again, 8 parallel paths 8 parallel paths, duplex winding. Okay, so now your current will be divided into first 8 parallel paths and duplex winding, so two times, right? Since in duplex winding you have two different coils connected to two slots, so your current in each coil would be reduced to IA by 16. Okay, and your parallel paths are still same. Now you are reducing the loading of current from each coil, but that is leading to increment in the slot current density. So slot density is more utilized. Okay, in slot current is increased. Okay, so let me conclude here. Slot is more utilized. This is the advantage. Okay, but slot current density will increase. This is advantage or disadvantage. You have to let me know about the second point, whether it is advantage or disadvantage. And third thing is your current loading of coil reduced. So it is certainly advantage. The second point is advantages or disadvantages. Slot current density is increasing. It means slot current is increasing. Okay, and it means there will be high loss I square R in each slot compared to the earlier case. And in that case, you will need more cooling to remove that much of heat that is generated in the slot, because slot is a compact space, right? So it is difficult to remove heat from that particular small space, right? So it we can see it as a drawback. Okay, so now is it fine? Is it clear to all of you that duplex winding, why there is double parallel path compared to simplex?
Sir, I have a doubt, sir.
Yeah, go ahead, please.
Sir, the two conductors in the same slot are under the
Hmm.
same pole and are moving in the same direction. So the
Yes.
induced current and voltage should be of the in same direction, sir. But here it is shown that one conductor has induced current outwards and the other is inwards. And the second point doubt is, sir, what is the difference between, sir, duplex and double layer winding, sir? In double layer winding, we also put two coil sides in one slot, sir.
Yeah, it is double layer binding only. Duplex is equivalent to double layer. There is not no any difference.
Sir, what about this difference in polarities, sir?
So let me. So see, this is the physical way how we connect our windings to the commutator, right? So if you connect, let me show. Uh, this is the physical way. How do you connect? But if you connect process, I do not have any physical or anything, but let me show you one figure. Mm, Okay, so I'm not able to find that figure. So what do I mean by it? Essentially, it's up to you whatever the polarity you want to have in your slot. Okay, so you are you are correct when you are saying that you can place same polarity. That is totally true. That is in your hand as a designer, right? So it is kind of, additive and subtractive polarity as we read in auto transformer, right? So if you place this particular uh, configuration of winding, if you design, then it will be subtractive polarity. Okay, this particular configuration is will be subtractive polarity. But as you are saying, you want to keep same nature of polarity in both cases. Oh, sorry.
No, sir, no, sir. I was not saying this case. I was saying that one slot, suppose one slot is under n pole,
Okay.
then both the conductors are moving in the same directions along the
Yes.
shaft. Sir,
Mm-hmm.
then the voltage
Yes.
induced in that slot on both the conductors should be same, sir. If it is inwards, then for both the conductors it should be inwards. If it is outwards, then for both the conductors it should be outwards.
Okay. So in that sense, you are saying that in DC machine, winding should polarity of both the windings should be same.
So both the
To
conductors in the same slot, sir.
Okay, in the same slots. Right. Right. Okay. Okay. Sorry, I messed this up with armature winding. So yeah, I'm sorry about that. You are correct here. In a stator, if you wound, you have the flexibility, but since these armature are placed on the rotor, so here I don't think you will have the flexibility, so you will have to go with the same kind of polarity. So thank you very much for pointing that error out. So Neeraj is correct here. In DC machine we have two wound with similar polarity in a slot. In a stator winding, if you do the armature winding, when you study the synchronous machine and induction machine, there you can place windings as you want. But in DC machine, our armature is rotating, right? So here we have to be careful with that. And here we should have the same polarity on in a single slot. So yeah, that might have confused you, but it is the thing. If there are any further doubt in this, I would be happy to clear it.
Sir, you said that this duplex winding and double layer winding are same.
Hmm.
But sir, here in duplex winding, the current is reduced by IA by 16.
Hmm.
But in double layer winding, it will be only reduced to IA by 8. Sir, why is there a
You are
difference, sir?
saying, okay, let me see what question saying. Okay, so could you please repeat in duplex winding what you are saying, and in double layer what you are saying? In duplex winding, you are saying that the number of parallel paths will be double of the number of poles, right? Am I correct?
Yes, sir. Yes, sir.
And in double layer winding, you are saying number of parallel paths are equal to
The pole, sir.
number of parallel paths are equal to number of pole. No, that is not correct. That is not
Okay, sir.
correct. Yeah, duplex winding and double layer wave winding, double layer windings are same. Okay, and here let me solve this problem quickly, otherwise it will create very much confusions. Okay, so first part, I hope it is clear. Let me further simplify it. IA is 120, and in first case simplex lap winding, okay, the number of parallel paths are equal to number of poles, and that will be 8, right? So it will be 15 ampere. I hope everyone is able to get this answer, right? In A part, I hope there is no doubt.
No, sir.
Okay, so let's move quickly to the B part. In B part, it is saying duplex lap wound. In duplex lap wound, as we saw just now, it will be double of the number of parallel paths, double the number of poles, and we know why, right? So here it will be 16 parallel paths. So IA will be here 120 by 16, which will be equal to 7.5 amps. Now in C part, B part is clear, right? It is correct for
Yes, sir.
everyone. Okay. C part is simplex wave wound. How many parallel paths will be here? Simplex wave wound? 2, as
Two.
we are continuously saying here. So IA will be 120 by 2, so 60. So from this, you can see that your current in each path are increasing according to the winding configuration you have applied, or in the question it is said, right? So I hope this question is correct. Let us move ahead with the next problem. So in this problem, you can see the configuration of windings. Also, they are connected to the slots to commutator, armature slots to commutator. So this machine is a two-pole DC machine, DC motor essentially, with 8 rotor coils and 10 turns per coil. The flux per pole is also given 6 milliweber. Okay. Now, if the motor is connected to a 12-volt DC car battery, what will be the no load speed of the motor will be? So what should be the approach for this particular problem? Anyone?
Sir, is the motor lap wound or wave wind?
That information is not there, and that should not be there as well because it is a two-pole motor.
Oh, oh, okay, sir. Sir, is it 12.5 rounds per second?
12.5 RPS, you are saying,
Yes,
or
sir.
18%? Okay, RPS. So mm, if I try to convert into RPM, then 12.5 into 60. So it will be around
750.
750 RPM. Okay, so 750 RPM. Hmm. Okay, so let us try to solve it and let us see what value will come. So, first thing is, okay, mm, since this motor has to operate at no load, okay, its back EMF is restricted or will be equal to terminal voltage, which is equal to 12 volt. Fine, and it should be equal to, we discussed in the last class, whenever EMF will come into picture and a speed, you have to quickly relate EMF with a speed. It will be K phi omega. Okay. Now we have to calculate this no load speed. I can write no load is equal to Vt by K phi. Vt is 12. K we don't know. Phi we know 6 milliweber. Now we have to identify the value of K, then we will be able to solve this problem. Okay. So what will be the value of K or expression of K?
Z multiplied by P by A.
Z multiplied with P by A. Are you sure?
Yes, sir.
Okay. I think I have derived in the last session. 2 pi will also come in the picture, right?
Okay, sir.
Since we are dealing with omega, 2 pi ns by 60. So 2 pi will also come in the picture. Now, that's why I think your answer would also be not accurate. So here number of conductors are given, right? Number of conductors are how much? How many number of conductors will be there in this particular question?
160.
160 number of conductors. Z is equal to 160. You are saying how you are saying 160?
Sir, there are 8 coils. Each coil would have two coil sides. That gives 16. And each coil, because there are 10 turns in each coil side will contain 10 conductors. Then 16 into 10, 160.
Okay. Okay, you are correct till this point, but there are something that you have to consider. Okay, so two conductors per turn, you are correct. Two conductors per turn. Two conductors per turn, and there are four turns per coil, right? In each coil, there are number of turns will be four. So let me into so but here in this question, figure is very important, right? So the effective or the active number of conductors we want from this figure. So those conductors will only participate in the generation of EMF which are actively under the influence of your magnetic poles. So at any time or any point of time, you can see these poles and these poles. These two armature poles are not under the influence of your magnetic field. So according to the Lorentz law or this Maxwell rule also, if you recall, these are perpendicular to the your magnetic field. Your magnetic field is flowing in this manner, and they will not be able to cut that conductor, or those portion will be not linked to the field magnetic flux that is generated by our stator field winding or stator magnetic field. So we have to remove that from the count of the number of conductors. Are you getting where it is leading? Where we can do mistakes? Neither, I think you solved.
We have to
So
remove that two coils
uh,
which are in between the two poles.
yes, yes, yes. So here I have to write six coils into two conductors per coil, two conductors per turn, and the number of turns are 10, right? So 12 into 10, 120 conductors. Sorry, 120 will be the number of conductors here. So in examination, they can test your theoretical concepts as well as numerical concepts. So if you are you are relying only on your formula, right? Your, you know, uh, your memory to just recall the expression and immediately apply in the question, you might miss out on certain marks. So it is very important, right? So here
Okay, sir.
120 number of conductors into number of poles were 2 divided by 2 pi into, anyway, a will be equal to 2. So here it will be 60 by pi, and it will, let us leave in the form of 60 by pi, it will be convenient. Okay, now we have to find out the omega no load. That was 12 divided by omega no load is equal to 12 divided by 6 into K is 60 by pi into 1000. So it will come out to be 104.72 radian per second. Is this value correct, Neeraj?
Yes, sir. Yes, sir.
Great, great. So I hope we are able to solve first part. Okay. Any doubt, anyone in the first part? If not, then we will move to the second part. If the motor is loaded down so that it consumes 600 watts from the battery, what will be the induced torque of the motor be? So it is asking for torque, right? So immediately what should come in your mind?
Torque is equal to K phi I.
Yes, perfect. So torque will be equal to K phi IA. Now K we know, 60 by pi. Phi we know, 6 milliweber. IA, do we know IA? No, IA we don't know. So IA we don't know. But from the data given in the problem, can we calculate IA?
No, sir. I think resistance value is not. Yes, sir. There is
Resistance is,
power
yes,
and voltage is
power
are
is
given.
equal to VB into IA. So VB is 12 volt into IA is, I don't know. It will be equal to 600. So IA will come out to be 50 amps. Now I just need to plug in that value 60 by pi into 6 into 10 raised to power minus 3 into 50, and it will come out to be how much? 50 into 60 by pi into 6. It will come out to be 5.73 Newton meter. I hope you guys are also getting the same value.
Yes, sir.
Great. Any final doubt in this part, this problem?
Sir, here we had to reduce the number of coils, sir. Is it necessary to do this reduction in every question or just in those cases where there are two poles involved?
Mm, wherever figures are given, okay, and, and if figures are not given, then you can conclude from questions. Are there any information provided in the problem that is dealing with the number of active conductors? Okay, so generally in most of the questions it won't, but it is always better that you pay attention on the minute details provided in the question, right? So in this, that's why I took this question, because it is our natural tendency. Had I been at the place of yours as well, I would have done the same mistake, because I already by hearted this formula is equal to uh, this k phi omega, and k is equal to zp by 2 pi a. and immediately I calculate Z is equal to number of turns per coil into number of turns into this number of conductors. But when you are very well aware of where can I do the mistake, you should have that kind of mindset. Always be doubtful, always be suspectful that I can be wrong in this problem. There can be any catch where I can fall, right? So if with that mindset you can point it that where this question want to get me wrong, and from that thing I think you can uh, end up with correct solution.
Sir,
Yeah,
if there will be four pole, then that conductor will come in active region.
yeah, definitely. In that case, that conductor will come in the active region. Yeah,
Okay.
but there is another it is not certainly guaranteed that in fourth pole all the conductors will come under the influence of your field MMF. Why? Because width of this north and south pole can also be reduced. It will be such a smaller that some conductors are not getting linked by field MMF, right?
Sir, is there any formula that takes account of this situation, sir? And we could
Uh,
directly apply and get the.
Unfortunately, there is not, because this is an analytical question. So you have to analyze based on the basis of whatever you have in your front. So unfortunately, there is not. So I cannot provide, and this you just have to judge it.
Whenever
Okay.
there is a
And sir,
diagram, we have to take care of it.
Yes, yes, yes. Yeah,
Okay, sir.
sir, I have a doubt.
yeah. Go ahead.
Sir, practically how we can analyze this conductor is in active region or out of field region.
Uh, Not in practically, even in the simulation also, if you do, uh, I think I had promised you to show the simulation. I completely forgot that. But
Yes,
okay,
sir.
so you have my number. I think you guys have my number or email ID.
Yes, sir.
Before next session, just one day before, if you could please remind me of a simulation so that I could show you some simulation. So on the basis of simulations, you can analyze that which poles or which armatures are not getting. So you will be able to see these flux lines. Like I drawn here the arrows, you will be able to see those flux lines. So with the help of that, we become sure that okay, so that conductor will not get linked and all. Okay, so if I will show you the simulation, then I think it will be much more visual.
Yes, sir.
Okay. Any other
Mm.
doubt in this particular question?
Sir, in the books, it is always described as the flux per pole is divided in the armature into half, sir, and this half flux goes to the adjacent pole. When the flux is flowing in such path, then every conductor in the armature should be linked, sir. There should be no conductor left out of the influence of the magnetic field. Then each conductor will participate in contribute in that in EMF generation.
Yeah, you are correct. See, where you are correct that each conductor will participate in generation of EMF, but at different instant of the time. Okay, not at the same instant of time. Let's see, this armature is rotating, right? This will rotate,
Yes, sir.
but when this portion will come under the influence of this magnetic field, then it will definitely generate the EMF. But at this particular instant, at this particular position, it will not happen for that portion only. For after certain millisecond or microsecond, some other portion will go there and that will get without link.
Yes, I understood this case of sir two poles, sir. But when
Uh-huh.
there are more than two poles, sir, four pole or six poles, suppose,
Yes, yes.
then the flux per pole from suppose the flux per pole from the north pole is divided when it enters the armature into half, and half goes to the s pole in its left side, and half of the flux goes to the right s pole in the right side. When flux flows in, sir, this manner, then
Mhm.
all the conductors will be linked, sir, with the magnetic field. If it draws are four poles or six poles or
Okay, so let
more.
me take a figure of four poles. Okay, then it will be clear. So let me take if I have four pole figure or not. Okay, so I have one four pole figure.
Sir, this question you prepared.
Uh, what you prepared means for what?
M- Means, sir, you you did
Yeah, go
ready
ahead.
this question for us.
No, no. Actually, I took this question from the textbook.
Okay.
I did not prepare the question. I do not need to because there are many, where great authors have already created such questions for us. So I
Sir,
don't
can
need.
you see my image, sir?
Yeah, definitely. I can see your image. Yeah,
Sir,
yeah.
here
Great.
the
That's great.
flux is getting divided, sir.
Yes,
And
yes.
in such case, sir, the
Hmm.
conductors which fall in the interpolar region are also getting linked, sir. Then they will also contribute in EMF generation, sir.
Okay, so that's what you meant. Yeah, yeah. Let me think over that. So, mm, hmm. Yes, yes, you are correct. But it will be more clear since we are not able to visualize armature conductors. But yeah, according to this flux path, it is certain that those conductors placed in interpolar region at any sort of time, they will also be linked. Okay, so
Okay.
if if we draw the conductors, then it will be much clear. So let me see if I have. Yeah, you are correct. I think you are applying the knowledge of the DC machine practically. So let me take this figure for you. So this is a four pole, right?
Yes, sir.
Here, here, this flux will have to travel, right? This should be the path.
So please excuse me for a minute, sir.
Definitely, definitely. Take your time.
Sir, figure is not visible.
Hello, Deepak.
Yes, bro.
What is happening here?
I think sir has gone somewhere.
Okay, then let's
Bro,
wait.
you are pass out or you are doing BTech currently or you are pass out.
I'm pass out.
In which year?
Take a guess. How do I look? How old do I look?
I think 2020.
You're wrong.
In which year?
Uh,
You can say to me. You can say.
why all this is getting recorded? Let's get back to the main topic.
Yeah, so you guys can interchange numbers among yourself and you can discuss. Okay, so let's get back to the topic. Yeah, so Neeraj's question was that in such cases, interpolar regions can also be linked, but yeah, they can link. But you see from this particular direction, right? There might be possibility of living of being some person left in linking if the machine will be large, right? If you are dealing with very large machine, in such scenario, you have to provide higher number of slots. And if you will provide that high number of slots, if instead of 16 it will be 32, then there are possibility that one slot pitch will be left out. So there are possibility. It is not that in case of higher number of poles, or it is guaranteed that all of the conductors will be linked, right? Uh,
Yes,
are
sir.
you getting? Are you getting, Neeraj? Yeah,
Yes, sir. Sir, I have one more point, sir.
yeah,
So the armature is constructed from good magnetic permeability material,
yes,
so that there is a good flow of generous flow of magnetic flux,
yes,
and it also influences the path the magnetic flux takes, sir. So
yes.
then, in case if the conductors are embedded in these armature, then mm, it is likely that almost all of the conductors will be linked by flux lines. Some may be more, some may be less, but every conductor should be linked.
Yes, yes. Generally, see uh, the design objective is itself that all conductors should get linked. So it is the worst case when any conductors or any armature poles are left out of being linked from magnetic fields that are generated by your stator magnetic field. Okay, so yeah, we design in in uh, keeping in that mind that all conductors should get linked. Otherwise, you are underutilizing your armature. Your armature will be underutilized with bad design. So that's why
Yes.
I am saying there might be certain cases where design might be bad and some conductors might not get linked. So it depends again on the design. And as far as flux lines are concerned, dependent on magnetic material. Okay, so magnetic material, better magnetic materials mean it has the capability of handling high amount of magnetic flux. It means better magnetic material means,
Ferromagnetic material.
yeah, ferromagnetic materials. But what does physical meaning it implies? It does not imply that it will channelize all your flux and it will make link. No, that
So
is
high
the work.
magnetic permeability.
That is fine. It is first thing is that it's BR. Oh, sorry, it's B limiting Generally, it is 1.6 to 1.8 Tesla, right? Of
Yes, sir.
silicon steel. Of silicon
Yes.
steel, it is 1.6 to 1.8 Tesla. Okay, so I know another material which is cobalt steel. Okay, its name, if you go and search, Vacoflux. I think the manufacturer is Vacoder. So if you see, its B limiting is up to 2.3 Tesla, and its price is 50 times more, 50 times more of silicon steel. Okay, so better magnetic material means your steel is able to handle high magnetic loading. We always talk about electric loading. Here, magnetic loading means you are able to manage that much of high magnetic flux. So, if your steel are getting saturated at certain level, it means after that point, if you are providing higher magnetic field from either the stator winding or the stator magnets, it doesn't matter. It will not create any useful flux or any useful torque from that, because of the you have crossed the limitation of that material.
Yes, sir.
Okay, so yeah, so better material means you can increase the magnetic loading, but it does not certainly mean that it will link or it will uniformly channelize all the magnetic flux path. So it is the work of designer, that how to design that all the conductors are uniformly linked. So here comes the job of machine designers who design the machines. So I hope it might be a bit abstract, but in the next session, please remind me before the session so that I gather some simulation results on the basis of DC machine, such that you get better perspective of it. Okay,
Sure, sir.
definitely. Thank you. So any further
And
doubt in
sir,
this question? Huh, go ahead.
sir, practically the bindings are laminated on armature by machine, automatic machine, right?
Huh.
No, sir, I want
So
to just know that.
why windings are wound on armature, or why windings are wound on a stator, or why windings are wound on rotor? So which one is your specific question? Accordingly, I will answer. See, armature winding is known as the winding where we give the supply, right? Which will, what is the job of armature current? It provides the loading. See, you cannot have any torque production until you have two forces that are getting interlinked, FA, FF, and sine delta. And we try to keep this delta is equal to 90 to produce maximum torque. It is FA, FF, sine 90, and it will be armature MMF into field MMF, right? It will provide you the, it is in proportionality. If you remove the proportionality, you will have KFA. Right. So armature winding is the winding that creates a force, and at the time when you are loading your motor. Okay. So armature means essentially load that will flow into the load, and because of that load current, there will be a torque that will be generated in the winding to cater that load. Are you getting my point, Deepak?
Yes, sir.
Without two forces interaction, you cannot generate torque. So that's the basic principles of electromagnetics. Two forces have to interact with each other to generate the torque. So that's why we deal in terms of armature field and our magnetic field. So in general, armature field is responsible to supply to load, and our field winding is responsible to supply the magnetic field. But that cannot be generalized. If you read the AC machine topic, there you will see, or if you might be aware with synchronous machine, synchronous reluctance machine, right? With salient pole motors. Okay. So with salient pole motors, or if even with induction motors, let us say very simple motor, induction motor. In induction motor, do you provide any field winding? If you recall any concept from induction motor, or if you are aware with induction motor.
Yes, sir, I am aware of, but sir, there is a stator winding instead of this field winding.
No, not instead of field winding. There is only a stator winding. Here we have on a
Yes.
stator field winding and on rotor armature winding in the DC machine. But in induction machine, we have only armature winding that is placed on a stator. We do not have any field winding that is placed on either a stator or rotor. But still, that motor works very well, and that is the work power of our industry.
Yes, sir, but sir, that motor has also two winding. First is rotor and second is stator.
Hmm. Yeah. So on rotor, do you provide any supply?
No, sir, because there is a due to induction, there will be some torque occur.
Huh. That induction is coming from a stator only, right? So
Yes,
there
sir,
you have
yes.
to. Let me break it into very simple terms. There you are breaking your stator mmf, okay, a stator mmf into two parts, active and reactive. Okay, active portion is responsible to generate the torque, okay, and essentially your output power, and reactive proportion is responsible to create the rated value of magnetic flux in the machine. Okay, so and both work is being carried out by the stator armature winding in the case of induction machine. As far as DC machine is concerned, here we have dedicated separate field winding, okay, that is provided on the stator, okay, and armature winding that is carried on the rotor that is responsible to create your active output power or torque. So field winding proportion is responsible to generate the rated flux. That's why you tweak with the field voltage supply to control the flux in the machine, and you tweak with armature supply to control the output power. Right. So that's why we always say VT into IA. We don't say in DC machine output power is equal to or is equal to EFIA. We don't say it is equal to IA, EFIF. Have you seen output power is equal to EFIF? No, but this component will come when you compute the loss and efficiency. But this is not active component that is generating your power. Are you getting what I am trying to convey?
Yes, sir.
Yeah, so it will be much clear when I guess we discuss AC machines sometime. But these are basically concepts that there are some component that is required to generate magnetic field in the machine, because without magnetic field you are not able to transfer your input power to output power, because there must be some induction. And if you have established your relationship between all the, if you have coupled all the stator and rotor, because there are air gaps so they cannot rotate automatically, there need to a coupling force. And once you have coupled both the components, now it is in your hand at what torque, what force you want to rotate it. So I hope it is enough to understand that thing. So let us move ahead with the next problem. It is good that we are discussing some practical aspects as well, because they are also very important, and nowadays they are very much important. As you know, industrialization is increasing in our country, we must be aware of practical things. We should not just restrict ourselves to theoretical knowledge.
Sir,
Yeah, go ahead.
uh, sir, I have one doubt in practical reason.
Yeah, ask.
Sir, because currently I am in fifth sem, sir, so I am studying this DC machine, and when I I was performing the practical in my lab. So
Uh-huh.
DC machine was not run. Uh, that was a separately excited DC machine.
Yes.
So we were giving a fixed supply to the field and a variable supply to the armature, but that
Uh-huh.
motor was not running. Why?
Uh-huh. See, for this kind of things, there must be, I should have been present there. That's how I could have figured it out. But I think your lab instructor might be a suitable person to answer this because I am not able to see what are the setups there. So there might be
But
some,
sir,
uh, yeah.
But sir, my technician also available. They are also not able to run that motor, and everything was good because we were measuring the voltage at each particular point. So the voltage were going to the motor directly, but that motor was not running. I don't know why.
Mm, but uh, have have has that motor ever ran ever before?
Yes, sir. Means yesterday, next day that motor was run, and
Huh.
we were next days to run that motor. So in my way, from my ways that motor was not running.
Okay, so that might be anything can happen in lab. So in lab, any one wrong thing can hamper all of your experiments. So it is the job of your instructor and whoever the lab staff to see it and figure it out. Since they are seeing it, I am not seeing the machine, right? I can see the machines in my lab, but I cannot see machines in your lab. So it is very difficult to say anything or comment anything on it.
Okay, sir.
Okay. Okay. So let us focus on this problem. Uh, An 8-pole 25 kilowatt 120-volt DC generator has a duplex lap wound armature which has 64 coils, okay, with 10 turns per coil. Its rated speed is also given. Now we have to find out how much flux per pole is required to produce the rated voltage in this generator at no load. So I think it is replica of last question, this part. That similar question we have to again
Please, the
identify.
one
Sorry, I couldn't get to your, what did you say?
you're able to see this.
I think your voice is breaking or you are on mute. Something might be, or your internet connection might be
And
unstable. Am I audible? First thing, am I audible? It might happen at my side as well.
yes, sir.
No, sir, you are audible.
Okay, I am audible. I think there is some internet issue at Neeraj's end. So neither either you can rejoin the session, so it will resume, I guess. So let us compute this first. Uh, okay, so we know whenever we need a speed relation with EMF, it will be K phi omega. Okay, and here we are given in RPM, and this relationship with omega radian per second. Okay, this omega is radian per second. So first thing is that we have to convert it to pi n by 60, and it will come out to be 2 pi into 3600 divided by 60. So 120 pi that per second. And we have to identify this phi, but k we need to compute. K is equal to zp by 2 pi a, right? So how many number of conductors will be here? P we know 8, 2 pi is fine, and it is duplex lap wound. So how many parallel paths will be here?
So parallel path will be 16.
16, yes. Parallel paths will be 16. How many number of conductors will be?
So 1280.
1280. 1280 you are saying. Why? How?
Sir, because the armature contains 64 coils and
Yes,
each coil with 10 tons.
10 turns. Yes, so 640, right?
Yes, sir. And we know that each coil contains two conductor, two coil side.
Okay, so basically it is 64 coils into 10 turns per coil. And since it is a duplex winding, we have to multiply it with 2. So 64, it will be equal to 1280. You are correct. Yeah, so we are done with Z. We have P, we have A, we have 2 pi. So let us finish it. 1280 into 8 divided by 2 pi into number of parallel paths are 16. So how much it will come out to be? 1200 into 8 divided by 2
So
into pi,
203.82.
203.82. 203.82 you are saying?
Yes, sir.
Okay. So we computed K. Now next part is flux. Okay, flux is nothing but EMF divided by K into omega. So EMF will be equal to terminal voltage at no load, right? So it will be 120 volt divided by K is 203.82 into, I think some background noise is there, Deepak, on your side. So
Sorry, sir.
203.82. No problem. You just can mute full. So into omega is equal to 120 pi radian per second. So it will come out to be 1.56 milliweber
Yes, sir. Correct.
per pole. Okay, so we are done with part A. Now the next four parts we are leaving for you. Okay, you do solve these questions. You let me know the answer either in comments or in this teams or in the next session. If you face any difficulty also, you let me know. So
Uh,
I hope
Yes, sir.
they will be fine for you to solve because they are not very much difficult. Just be conscious that what are mistakes you can commit. Otherwise, they are pretty simple questions.
Okay, sir. Sir, answer. Yeah, you will tell me, or I will solve that. This only answer.
Use only answer you want. So okay. So in next session we start from the answer of this part. If they are correct, then fine. We move ahead with the next topic, and if they are wrong, then we will discuss these leftover four parts.
Yes, sir. Sure.
Okay. And please remind me for that simulation files. Okay, so I will keep that before 1 day or 2 day. If you remind, I will have that.
Okay, sir. I will remind you on WhatsApp, right?
Definitely, yeah, that would work. Fine.
Yes, sir.
So
Thank you, sir.
yeah, thank you very much. So it's now time to conclude the session. So thank you very much for attending. Have a good night. Bye.